Welcome back to the Nocturnal Astronomer. I'm your host, Atlas Reid. If you're new here, this channel exists for the quiet hours. Whether you're settling in for sleep, unwinding after a long day, or simply want something thoughtful drifting in the background while the world goes still, these explorations are designed to carry you gently through the deepest corners of the universe. Tonight, we are going somewhere very far from home, somewhere dark and cold and adrift. We are going to follow the worlds that belong to no star, planets that were born in the light and warmth of a forming solar system, then cast out into the void between the stars, wandering through interstellar space alone, perhaps forever. They are called rogue planets, free-floating worlds. Some are the size of Jupiter, some may be smaller than Earth. They travel without suns, without moons that orbit them by choice, without any destination. They are simply out there, drifting through the dark in numbers that may dwarf every star in the galaxy. Part 1. What a rogue planet is. A rogue planet is a planetary mass body that travels through space unbound to any star. It does not orbit a sun. It does not belong to any solar system. It moves through interstellar space on its own trajectory, governed only by the large-scale gravitational structure of whatever galaxy it happens to inhabit. The term rogue planet is the most common name used in popular astronomy, but scientists also refer to these objects by several other names. Free-floating planets, orphan planets, and interstellar planets are all terms that appear in the scientific literature, depending on the context and the research group involved. The definition has some nuance to it. To be called a planet rather than something else, an object generally needs to fall within a certain mass range. The upper boundary is particularly important. Above a certain mass, an object can sustain nuclear fusion in its interior, making it a star rather than a planet, even if it has no companion. The boundary between the most massive planets and the least massive stars is not perfectly sharp, but it generally falls around 13 times the mass of Jupiter. Objects between roughly 13 and 80 times Jupiter's mass are usually called brown dwarfs rather than planets. Below 13 Jupiter masses, the term planet becomes applicable, including for free-floating objects. Some scientists prefer to reserve the word planet specifically for objects that formed within a disk around a star, making origin part of the definition rather than just mass. Under this view, a free-floating object of planetary mass that formed in isolation like a star would not technically be a planet. The debate over terminology is ongoing. For the purposes of tonight's journey, we will use the term rogue planet broadly to include any planetary mass object wandering through interstellar space, regardless of exactly how it formed. What unites all of these objects is the same defining characteristic. They are alone. They have no star to orbit. they move through the dark on their own. The concept of a planet without a sun is counterintuitive to our ordinary understanding of what planets are. Every planet most people can name belongs to a solar system. The idea that planets might exist in vast numbers between the stars, invisible and unattached, expands the definition of what a world can be in a fundamental way. Rogue planets are not science fiction. They are a well-established prediction of planetary formation theory and have been confirmed by observation. The question is no longer whether they exist. The question is how many there are, where they came from, and what, if anything, is happening on their surfaces and in their interiors right now. The answer to that last question is more interesting than it might first appear. A world without a sun is not necessarily a dead world. The universe has more than one way to keep a planet warm, and some of those ways do not require a star at all. But we will get to that in time. First, we need to understand how a planet ends up alone in the first place. Part 2. How worlds are cast out. The most well-understood pathway to becoming a rogue planet begins inside a solar system. Planets form from disks of gas and dust that surround young stars. During the early chaotic phase of a solar system's development, newly formed planets interact gravitationally with each other and with remaining gas in the disk in ways that can dramatically alter their orbits. In a crowded young solar system, gravitational interactions between planets can be violent. A close encounter between two massive planets can fling one of them onto a highly elliptical orbit that carries it far from the star. Subsequent encounters, or interactions with the outer disk of gas and planetesimals, can strip the planet from the system entirely. Think of it like a game of billiards happening over millions of years. The balls are planets, and the table has no edges. When two massive planets pass close enough to interact strongly, the exchange of energy can send one of them flying off the table entirely, escaping the gravitational hold of their parent star and entering interstellar space. This process is not rare. Computer simulations of solar system formation consistently show that many planetary systems produce one or more ejected planets during the chaotic early phase. Some simulations suggest that our own solar system may have ejected a significant body during its early history, possibly a fifth giant planet that once existed between the orbits of Jupiter and Neptune. Jupiter plays a particularly important role in gravitational scattering within solar systems. Its enormous mass makes it an effective gravitational engine. When smaller planets or large rocky bodies pass too close to Jupiter, they can receive a gravitational kick that sends them onto escape trajectories. Jupiter has likely been responsible for clearing a great deal of material from the early solar system this way. The timescale for ejection can vary enormously depending on the specifics of the system. Some planets are ejected within the first few million years of a solar system's life, when gravitational interactions are most frequent and intense. Others may be destabilized over much longer timescales, hundreds of millions of years later, through slower accumulating gravitational nudges. The speed at which a planet is ejected determines how fast it will travel through interstellar space. A planet that barely escapes its parent star's gravity will move slowly relative to surrounding stars. One that receives a powerful gravitational kick may travel at a significant fraction of the typical stellar velocity in the galaxy, tens of kilometers per second. Once a planet leaves its solar system, the universe offers nothing to slow it down. There is no friction in interstellar space. The planet simply continues on its trajectory indefinitely, unless it passes close enough to another star to be gravitationally captured, which is extraordinarily unlikely given the vast distances between stars. The ejection scenario is the most commonly cited origin for rogue planets, but it is not the only one. There is a second pathway, one that does not require a solar system at all, and it comes from the same process that forms stars. Understanding that pathway requires a brief look at how stars themselves are born. Part 3. Born alone in the dark. Stars form when dense regions within molecular clouds, vast cold clouds of gas and dust, collapse under their own gravity. The collapsing cloud fragments into clumps, and each clump that accumulates enough mass will eventually ignite nuclear fusion and become a star. But the fragmentation process does not always produce objects massive enough to become stars. Some fragments produce objects in the mass range of planets. These objects collapse, heat up, radiate away their energy, and settle into dense, cold spheres that never ignite fusion. They form through the same basic process as stars, but end up as planetary mass objects simply because the initial fragment of gas was not massive enough. This is a well-documented phenomenon in astronomy. Observations of young star-forming regions have found free-floating objects with masses well below the hydrogen-burning limit scattered among the newly formed stars. These objects appear to have formed in the same way as their stellar neighbors, just from smaller initial fragments. Whether these objects should be called planets is part of the definitional debate mentioned earlier. They formed like stars, not like planets. They were never part of a disk around a parent star, but their masses fall in the planetary range, and they share the defining characteristic of all rogue planets. They are alone, and they are drifting. The two formation pathways, ejection from a solar system and direct formation in isolation, likely both contribute to the overall population of free-floating planetary mass objects in the galaxy. Distinguishing between them observationally is difficult because a planet formed in isolation and one ejected from a solar system would look essentially identical once both are traveling through interstellar space. One way astronomers hope to distinguish between these populations is through statistical analysis of mass distributions. Objects that formed like stars should follow a mass distribution similar to the low end of the stellar mass function. Objects ejected from solar systems should reflect the mass distribution of planets in the kinds of systems most likely to eject them. Another potential distinguishing factor is composition. Planets that formed in solar system disks may have different chemical signatures in their atmospheres compared to objects that collapsed directly from molecular cloud gas. Whether these differences would be detectable with current or near-future instruments is an active area of research. The existence of a direct formation pathway also raises an interesting conceptual question about where the boundary between a very small star and a very large planet truly lies. The universe does not sort its objects into neat categories. It produces a continuous distribution of masses, and the names we apply to different parts of that distribution reflect our frameworks as much as any sharp physical distinction. What the direct formation pathway makes clear is that the universe produces planetary mass objects in more than one way. Rogue planets are not simply the leftovers of failed solar systems. Some of them are, in a meaningful sense, their own kind of thing entirely. Solitary worlds that formed alone and have been alone ever since. Part 4. How many are out there? One of the most striking aspects of rogue planets is the sheer number that may exist. Early theoretical estimates and observational hints suggested that free-floating planets might be common. More recent observations have pushed those estimates higher still, to the point where some researchers believe rogue planets may be among the most numerous planetary mass objects in the galaxy. Estimating the population of rogue planets is difficult because they emit almost no light. They do not shine like stars. They do not reflect starlight the way planets in solar systems do, because there is no nearby star to reflect. Finding them requires either detecting the faint heat they emit or waiting for one to pass in front of a distant background star. The second technique, called gravitational microlensing, has been the most productive method for detecting rogue planets. When any massive object passes between Earth and a distant background star, the object's gravity bends and focuses the background star's light, causing it to brighten temporarily. The duration and shape of the brightening reveal information about the mass of the object doing the lensing. Short-duration microlensing events, lasting hours to days, correspond to objects of low mass in the planetary rather than stellar range. By monitoring millions of background stars continuously and looking for these brief brightenings, surveys can detect rogue planets passing through the line of sight, even though the rogue planets themselves are invisible. A major microlensing survey published in 2011 found evidence suggesting that Jupiter-mass rogue planets might be nearly twice as common as main sequence stars in the galaxy. If the Milky Way contains roughly 200 billion stars, this would imply hundreds of billions of Jupiter-sized rogue planets wandering through interstellar space. More recent surveys using improved techniques have refined these estimates. The Nancy Grace Roman Space Telescope, designed in part specifically for microlensing surveys, is expected to dramatically expand the catalogue of detected rogue planets and provide much better constraints on their population across different mass ranges. Some estimates, when extrapolated to include smaller rogue planets in the Earth mass range, suggest that there may be more rogue planets in the galaxy than stars. The total number, including all masses down to the size of small rocky planets, could be in the trillions. The interstellar medium, long thought of as largely empty, may be quietly populated with drifting worlds. These numbers carry enormous implications for how we think about the universe. The picture of planetary systems as the primary home for planets, with interstellar space as an empty void between them, may be fundamentally incomplete. The spaces between stars may be filled with wandering worlds, most of them cold and dark and entirely undetected by current instruments. The uncertainty in these estimates is significant. Microlensing surveys are sensitive to certain mass ranges and certain distances more than others. Extrapolating from what is detected to the full population requires assumptions that are difficult to verify. But even the most conservative estimates suggest that rogue planets are remarkably common, and the more optimistic ones suggest they may outnumber everything else. Part 5. Moving Through the Dark. A rogue planet travelling through interstellar space inhabits an environment that is almost nothing like the one it formed in. The space between stars is extraordinarily sparse, cold, and quiet. Understanding what that environment is like helps paint a picture of what the journey of a rogue planet actually involves. The interstellar medium is not a perfect vacuum, but it is close. It contains a thin mixture of gas, mostly hydrogen and helium, along with traces of heavier elements and tiny solid particles called interstellar dust grains. The density of this material is extraordinarily low, typically only a few atoms per cubic centimeter, compared to the roughly 10,000 billion molecules per cubic centimeter in the air we breathe. A rogue planet moving through this environment encounters essentially no resistance. The interstellar medium is too sparse to exert any meaningful drag on a planet-sized object. The planet travels in a straight line at constant speed, unless it passes close enough to a massive object, a star or another planet, to be deflected gravitationally. The temperature of the interstellar medium varies considerably depending on location and the influence of nearby stars and other energy sources. In the cold, dense regions of molecular clouds, temperatures can drop to only 10 degrees above absolute zero. In the warm, diffuse regions between clouds, temperatures can reach thousands of degrees, though the gas is so thin that this heat carries almost no energy. A rogue planet moving through this environment receives essentially no external heat from it. The planet is on its own thermally. Whatever warmth it retains comes entirely from its own internal sources: the residual heat of formation, the decay of radioactive elements in its interior, and in some cases, the tidal forces of any moons it might have retained after ejection. The speed at which a rogue planet moves through the galaxy depends on its history. A planet ejected violently from a solar system during a close encounter with a massive planet may travel at tens of kilometers per second relative to the local standard of rest. A planet that was gently nudged out of its system over a long time may move more slowly. For comparison, the Sun moves through the galaxy at roughly 220 kilometers per second relative to the galactic center, and at roughly 20 kilometers per second relative to the average motion of nearby stars. A rogue planet ejected from a solar system in the Sun's neighborhood would travel at roughly similar speeds relative to the galactic center. At these speeds, crossing the distance between two typical nearby stars would take on the order of 100,000 years. The galaxy is roughly 100,000 light years across. A rogue planet traveling at typical interstellar speeds would take billions of years to cross the galaxy from one side to the other, assuming it traveled in a straight line, which it would not. The trajectory of a rogue planet through the galaxy is not a straight line. The galaxy itself has a gravitational structure, the combined pull of hundreds of billions of stars, dark matter, and other mass distributed throughout the disk and halo. A rogue planet follows a complex curved path through this gravitational landscape, rising above and dipping below the galactic plane as it orbits the galactic center over hundreds of millions of years. Part 6. What keeps them warm? When most people imagine a planet without a sun, they imagine a frozen, lifeless world, a ball of ice drifting through the darkness at temperatures close to absolute zero. For many rogue planets, this picture is essentially correct. But for others, and this is where things get genuinely interesting, the story is more complicated and more surprising. The primary internal heat source for any planet is the residual heat accumulated during formation. When a planet forms from a collapsing cloud of gas or from the accretion of material in a protoplanetary disk, the process releases an enormous amount of gravitational energy. This energy heats the planet's interior, and the heat then slowly radiates outward over billions of years. For a large rogue planet, particularly one in the mass range of Jupiter or above, this internal heat can be substantial. Jupiter itself radiates about 1.5 times as much energy as it receives from the Sun. This excess energy is the leftover heat from Jupiter's formation, still slowly leaking out of its interior after 4.5 billion years. A free-floating planet the size of Jupiter, far from any star, would still be radiating this internal heat into space. It would be warmer than the surrounding interstellar medium, possibly significantly warmer, depending on its age and mass. The more massive the planet, the more gravitational energy was released during formation, and the more heat it has to radiate away. A free-floating planet the size of Jupiter far from any star, would still be radiating this internal heat into space. It would be warmer than the surrounding interstellar medium, possibly significantly warmer, depending on its age and mass. The more massive the planet, the more gravitational energy was released during formation, and the more heat it has to radiate away. A free-floating planet the size of Jupiter, far from any star, would still be radiating this internal heat into space. It would be warmer than the surrounding interstellar medium, possibly significantly warmer, depending on its age and mass. The more massive the planet, the more gravitational energy was released during formation, and the more heat it has to radiate away. A free-floating planet the size of Jupiter, far from any star, would still be radiating this internal heat into space. It would be warmer than the surrounding interstellar medium, possibly significantly warmer, depending on its age and mass. The more massive the planet, the more gravitational energy was released during formation, and the more heat it has to radiate away. The second internal heat source is radioactive decay. Rocky planets contain trace amounts of radioactive elements, primarily uranium, thorium, and a form of potassium left over from the stellar processes that produced them. As these elements decay over billions of years, they release energy that heats the planet's interior. This is the same process that keeps Earth's interior warm and drives plate tectonics and volcanic activity. For a rogue rocky planet of roughly Earth size and composition, radioactive decay alone is sufficient to maintain a warm interior, even in the complete absence of starlight. The surface of such a planet, exposed to the cold of interstellar space, would be extraordinarily cold. But deep beneath the surface, temperatures could remain well above freezing. This brings us to one of the more remarkable possibilities in rogue planet science. If a rogue planet of roughly Earth's mass retains a thick atmosphere of hydrogen, which can act as an extraordinarily effective insulating blanket, the surface temperature could potentially remain above the freezing point of water, despite the complete absence of a star. A 2009 study by researchers including David Stevenson explored this possibility and found that an Earth-mass planet with a dense hydrogen atmosphere could maintain surface temperatures capable of supporting liquid water for billions of years, even as a rogue planet. The hydrogen atmosphere would trap the internal heat radiating from the planet's surface and prevent it from escaping into space. The implications of this finding for the possibility of life are significant, but they also simply highlight something beautiful about the universe's creativity. The conditions for liquid water, long assumed to require proximity to a star, can in principle be maintained by nothing more than the right kind of atmosphere and a planet's own internal warmth. A world can carry its own greenhouse wherever it goes. Part 7. Atmospheres and Ice. The atmospheric fate of a rogue planet depends heavily on its mass, its temperature history, and the type of atmosphere it carried when it left its solar system. For large, Jupiter-like rogue planets, retaining a thick gaseous envelope is relatively straightforward. Gravity is strong enough to hold light gases like hydrogen and helium, and the internal heat keeps the atmosphere from freezing solid. For smaller rogue planets, the situation is more precarious. Earth-mass planets have weaker gravity and lose atmospheric gases more easily through a process called atmospheric escape, where individual gas molecules moving fast enough at the top of the atmosphere can exceed escape velocity and drift off into space. Without the solar wind and radiation that also drive escape, a rogue planet's atmosphere might actually be more stable than a comparable planet in a solar system. The temperature at a rogue planet's surface determines what can exist there in a liquid or gaseous state. At temperatures far below the freezing point of water, any water present would be locked in ice. At temperatures cold enough, even carbon dioxide, which remains a gas down to about -78 degrees on Earth, would freeze out of the atmosphere entirely. Some rogue planets may carry oceans of liquid beneath thick, icy surfaces. If the interior remains warm enough from radioactive decay and residual formation heat, the pressure at the base of a deep ice layer could maintain liquid water even if the surface is frozen solid. This is not so different from the situation on several moons in our own solar system. Europa, one of Jupiter's moons, maintains a liquid water ocean beneath its icy surface, not through radioactive decay, but through tidal heating, the flexing of the moon's interior caused by Jupiter's gravity. A rogue planet ejected from a solar system might carry moons with it, and those moons could continue to experience tidal heating from the planet's gravity long after ejection. The surface of a rogue planet exposed to interstellar space would be bathed in cosmic rays, high-energy particles streaming through the galaxy from supernova remnants and other energetic sources. Without the magnetic field of a parent star to deflect them, and depending on the planet's own magnetic field, these cosmic rays would bombard the surface continuously. At very cold temperatures, surfaces would accumulate layers of frozen gases. Nitrogen, carbon monoxide, and other volatiles that exist as gases at warmer temperatures would freeze onto the surface, building up frost layers that might reach considerable depth over billions of years. The chemistry of these frost layers, subject to ongoing bombardment by cosmic rays, could be surprisingly rich. Laboratory experiments have shown that mixtures of simple frozen molecules, when subjected to radiation, can produce more complex organic molecules. A rogue planet's frozen surface, bombarded by cosmic rays for billions of years, might accumulate a layer of chemically complex material on top of the underlying ice or rock. Whether any of this has biological relevance is deeply speculative, but the chemistry itself is real. The long-term atmospheric evolution of rogue planets is not well understood because we have not yet been able to study any rogue planet in detail. Current detections are based on reveal little about composition or structure. The atmospheres of rogue planets remain largely theoretical territory, informed by models and by analogy with better studied objects. Part 8. The Visitor from Outside. In 2017, astronomers detected the first confirmed interstellar object to pass through our solar system. It was a small body, roughly 400 meters across, detected by a survey telescope at the University of Hawaii as it swept through the inner solar system on a trajectory that was unmistakably hyperbolic, meaning it was moving too fast to be bound to the sun and had come from outside. It was given the designation Oumuamua, a Hawaiian word meaning roughly a messenger from afar arriving first. Its origin outside the solar system was not in question. The mathematics of its trajectory traced it back to the general direction of the constellation Lyra, and its speed as it entered the solar system was far too high to have originated from within it. Oumuamua was unusual in several respects. Its brightness varied dramatically as it rotated, suggesting an elongated shape, possibly 10 times longer than it was wide, unlike any solar system body of comparable size. It also showed a slight deviation from the trajectory that gravity alone would predict, as if something was giving it a small additional push. The most straightforward explanation for this extra push in small solar system bodies is outgassing, the release of gases from ices heating up as the object passes near the sun. But no outgassing was detected from Oumuamua, despite sensitive searches. Several alternative explanations were proposed, including radiation pressure on an unusually thin, flat object, and the possibility of trapped hydrogen slowly escaping from its interior. 2019 brought a second confirmed interstellar visitor, a small comet designated Borisov after the amateur astronomer who discovered it. Unlike Oumuamua, Borisov appeared much more like a typical solar system comet, showing clear outgassing and a coma of gas and dust. Its composition appeared broadly similar to comets from our own solar system. These two objects were not rogue planets. They were far smaller, more like interstellar debris, or the equivalent of asteroids and comets scattered between the stars. But their detection confirmed that interstellar objects do pass through our solar system, and that with sufficiently sensitive surveys, they can be detected. The detection of Oumuamua and Borisov raises the question of how often objects of all sizes pass through our solar system from interstellar space. Statistical analysis suggests that small interstellar objects like these pass through the inner solar system relatively frequently, perhaps one or more per year. The reason so few have been detected is simply that most are too faint and pass through too quickly. A true rogue planet passing through the solar system would be detectable at far greater distances. Its gravitational influence alone would be measurable if it passed close enough. At planetary distances from the Sun, it would be detectable optically. The probability of such a close passage on any human timescale is vanishingly small, given the vast distances involved, but over geological timescales, such encounters are possible. The interstellar visitors detected so far are a reminder that the solar system is not isolated. It moves through a galaxy populated with debris, ejected material, and drifting worlds. The interstellar medium is not empty. It contains the material shed by billions of years of solar system formation, evolution, and disruption, drifting silently between the stars. Part 9. Captured Worlds. While the ejection of planets from solar systems is well established, the reverse process, the capture of a rogue planet by a solar system, is also theoretically possible, though far more difficult to achieve. Capturing a freely moving object into a stable orbit requires extracting energy from the incoming body, and in the emptiness of space, opportunities for that are limited. In the early solar system, when a disk of gas was still present, the drag provided by that gas could, in principle, help capture incoming objects. A rogue planet or large body passing through a young solar system surrounded by a dense gas disk might lose enough energy through interaction with the disk to be deflected onto a bound orbit. This capture mechanism would only operate during the first few million years of a solar system's life. Three-body gravitational interactions offer another capture pathway. If a rogue planet passes through a solar system at a time when it can interact closely with a large planet like Jupiter, the three-body exchange of energy might leave the rogue planet in a bound orbit, while Jupiter is pushed to a slightly different orbit. This process is rare, but physically possible. Some astronomers have speculated that certain unusual objects in the outer solar system may be captured interstellar bodies. The hypothesis has been applied to some of the distant, highly inclined or retrograde objects found in the outer reaches of our solar system, bodies whose orbits are difficult to explain through the standard formation and migration history of the solar system. Whether our solar system has ever captured a rogue planet or large interstellar body remains an open question. Definitive proof would require identifying an object whose composition or orbital properties are inconsistent with any origin within our solar system. Current observations have not yet provided such a clear case, though some candidates have been proposed. The reverse journey is also worth considering. Some material from our own solar system has certainly been ejected into interstellar space over the billions of years of gravitational interactions that have shaped the outer solar system. Small bodies, comets, and planetesimals have been scattered onto escape trajectories throughout the solar system's history. Whether any fully formed planet has ever been ejected from our solar system is a question with a surprising answer. Several lines of evidence suggest that the outer solar system may once have been more crowded than it is today. The Nice model of solar system evolution, developed in the early 2000s, proposes a period of instability in the outer solar system that resulted in the ejection of one or more large bodies. If a planet-sized body was indeed ejected from our solar system in the distant past, It is now a rogue planet, drifting through interstellar space. It carries material formed in the same disk that formed Earth, Jupiter, and the other planets. It is, in a strange sense, a sibling world, born in the same place as our own planet, but separated by billions of years and uncountable distances. That possibility has a particular kind of resonance. The universe is full of worlds that were once part of a system like ours and are now alone. The night sky, if we could see them, would reveal a silent population of wandering siblings, each one a record of a solar system's turbulent youth and the gravitational forces that shape planetary architecture. Part 10. Could life survive? The question of whether life could exist on a rogue planet is one of the more speculative but genuinely grounded discussions in astrobiology. The conditions required for life as we understand it are not perfectly known, but liquid water, a source of chemical energy, and some degree of stability over long timescales are generally considered necessary ingredients. As discussed in the earlier part about warmth and atmospheres, a rogue planet of the right mass and composition could, in principle, maintain liquid water beneath its surface, beneath thick ice, or even at the surface if it retains a dense hydrogen atmosphere. The absence of a star removes the most obvious energy source, but does not remove all energy sources. Hydrothermal vents on the ocean floor of Earth support ecosystems that receive no energy from sunlight. These ecosystems are driven entirely by the chemical energy released as water interacts with hot rocks at the boundary between the ocean floor and the planet's warm interior. The energy source is geochemical, not solar. A rogue planet with a warm interior, a subsurface liquid water ocean, and seafloor geology could, in principle, support analogous ecosystems. The water would circulate between the warm interior rocks and the liquid ocean, carrying dissolved minerals and releasing chemical energy at vent sites. Whether life would actually originate under such conditions is entirely unknown, but the physical conditions would not rule it out. The longevity of these conditions on a rogue planet is a key consideration. Earth's interior has remained warm for over 4 billion years, driven by radioactive decay and residual formation heat. A rogue planet of similar mass and composition would have similar longevity. The conditions for subsurface liquid water and hydrothermal activity could persist for billions of years after ejection. One significant challenge for life on a rogue planet is the period of ejection itself. Being flung out of a solar system would involve gravitational disruptions and potentially significant changes in the planet's thermal environment as it moved from proximity to a star to the cold of interstellar space. Whether organisms could survive this transition, if they existed before it, is unclear. Another challenge is the absence of the kind of energy input from a star that drives atmospheric chemistry and, on on Earth, photosynthesis. Life on Earth is overwhelmingly powered by sunlight. The shift to purely geochemical energy would represent a fundamental constraint on the complexity and diversity of any ecosystem that might arise. Some researchers have pointed out that life does not necessarily need to resemble life as we know it. In environments with very different energy sources and chemistry, life might take forms that are difficult to anticipate from our Earth-centric perspective. Speculating about the specific forms life might take on a rogue planet goes well beyond what current science can support, but the question of whether it could exist in any form remains genuinely open. The astrobiological interest in rogue planets is partly practical. If life can arise and persist in the complete absence of a star, then the number of potentially habitable worlds in the galaxy expands dramatically. Life would not be constrained to the narrow habitable zones around stars. It could exist anywhere in the galaxy where the right conditions obtain, including in the vast cold spaces between solar systems. Part 11. Finding them. Detecting rogue planets is one of the more challenging observational problems in modern astronomy. These are objects that emit very little light, reflect no starlight because there is no nearby star to reflect, and move through regions of space that are not routinely targeted by telescopes looking for something specific. Finding them requires indirect methods and surveys designed with them in mind. Gravitational microlensing, as mentioned earlier, has been the most successful detection technique to date. When a rogue planet passes between Earth and a distant background star, its gravity briefly bends and brightens the star's light in a characteristic way. The event typically lasts only hours to days for a planet mass object, compared to weeks or months for a stellar mass lens. Microlensing surveys require monitoring enormous numbers of background stars continuously. The center of the galaxy, where stars are densely packed, provides the richest field for such surveys. Several ground-based surveys have operated in this mode, most notably the optical gravitational lensing experiment, a Polish-led survey that has been operating for decades and has accumulated a rich catalogue of microlensing events. The Rubin Observatory, currently under construction in Chile, with first light anticipated in the mid-2020s, will conduct the Legacy Survey of Space and Time, monitoring billions of stars repeatedly and with high precision. Its sensitivity and sky coverage make it well suited for detecting microlensing events from rogue planets across a wide range of masses. Direct imaging of rogue planets is possible for the most massive and youngest examples. A recently formed massive rogue planet retains more of its formation heat and therefore glows more brightly in infrared light than an older, cooler one. Infrared surveys of star-forming regions and young stellar associations have identified numerous free-floating planetary mass candidates in this way. The James Webb Space Telescope has opened up new possibilities for studying these young free-floating objects. Its extraordinary infrared sensitivity allows it to characterize characterize the atmospheres of planetary mass objects in ways that were not previously possible, measuring temperature, detecting molecules in the atmosphere, and comparing the properties of free-floating objects with those of planets in solar systems. A particularly productive approach has been to survey young stellar clusters and associations, where free-floating planetary mass objects formed relatively recently still glow brightly in infrared. A 2023 survey of a young stellar association in the constellation Orion identified a population of free-floating planetary mass objects, including some that appeared to be in pairs, a surprising and theoretically challenging finding. These paired, free-floating planets, if confirmed as genuine gravitationally bound pairs rather than chance alignments, pose interesting questions for formation theories. Forming a gravitationally bound pair of planetary mass objects through direct collapse from a molecular cloud fragment is theoretically possible, but constrained. Their existence adds another layer of complexity to the already rich question of how rogue planets come to be. The next major step forward in rogue planet detection will likely come from the Nancy Grace Roman Space Telescope, whose microlensing survey is expected to detect hundreds to thousands of free-floating planets across a wide range of masses, including objects as small as Mars. This survey will provide the most statistically robust census of the rogue planet population yet attempted, and will substantially clarify the total numbers and mass distribution of these wandering worlds. Part 12. The Long Dark Ahead. To follow the future of rogue planets is to follow one of the quieter storylines in the long future of the universe. While stars will eventually exhaust their fuel and leave behind white dwarfs and neutron stars, and while galaxies will merge and the interstellar medium will gradually be consumed, rogue planets will simply continue doing what they have always done: drifting. A rogue planet that survives the current age of the universe without being captured by a star or destroyed by a collision has a long future ahead of it. The universe is currently about 13.8 billion years old. Most rogue planets will outlast the stars that formed the material they are made of by many orders of magnitude. As the stelliferous era, the age of stars, eventually draws to a close over the next several trillion years, the galaxy will gradually fill with stellar remnants. The last red dwarf stars will burn out and become white dwarfs. New star formation will slow and stop as the available gas is consumed. The galaxy will grow darker and quieter over timescales that dwarf anything in current cosmic history. Through all of this, rogue planets continue their wandering. In a galaxy growing gradually emptier of active stars, the probability of a rogue planet passing close enough to a stellar remnant to be captured decreases. The wanderers become more and more permanently solitary as their potential gravitational companions slowly disappear. The internal heat of rogue planets will gradually diminish over these timescales. Radioactive elements decay, and their contribution to interior heating The most long-lived radioactive heat sources, thorium and uranium, have half-lives in the billions of years, but even they will be substantially depleted over trillions of years. Rogue planets will slowly cool from the inside. As interior heat diminishes, any subsurface oceans will begin to freeze. The freezing front will move slowly inward over billions of years, converting liquid water to ice from the outside in. Whether the very deepest regions, under the most pressure, maintain liquid water longer than the shallower layers is a function of the specific pressure and temperature profiles inside the planet. Eventually, after timescales that make the current age of the universe feel brief, even the most well-insulated rogue planet interiors will cool to temperatures where liquid water can no longer persist anywhere within them. The planet will be, from its surface to its core, a frozen solid, a ball of ice and rock and possibly crystallized materials, drifting silently through whatever the universe has become by then. In the far future era, when white dwarfs themselves are cooling toward black dwarfs, rogue planets will still be drifting. They will have been cooling alongside the stellar remnants, moving through a universe that is darker, more spread out, and quieter than anything we can meaningfully imagine from our current vantage point in cosmic history. The final state of a rogue planet, like the final state of a white dwarf, is a cold, dark, inert object drifting through an increasingly empty universe. But while white dwarfs were once the burning hearts of stars and carry that history in their dense interiors, rogue planets were once worlds. They formed in warmth and light, surrounded by the activity of a young solar system, and then were sent out into the dark. What they carry with them across all those unimaginable distances and timescales is the matter of worlds, and they carry it forever. And on that note, we come to the end of tonight's journey through the long, wandering dark of rogue planets. From the chaotic gravitational billiards of young solar systems that send planets flying into the void, to the cold interstellar spaces they inhabit for billions of years, to the surprising possibility of warmth and liquid water far from any star, to the distant future when these wandering worlds drift through a universe that has grown very nearly silent. Rogue planets are not the universe's most dramatic objects. They do not explode or collapse or spin hundreds of times per second. They simply drift through the spaces between stars, through the slow cooling of cosmic time, through an enormous and patient darkness that has no particular end in sight. And in that drifting, there is something worth sitting with for a while. Whether you made it all the way through, or drifted off somewhere around the subsurface oceans and cosmic ray frost, I hope the cosmos gave you a little peace tonight. Thank you so much for joining